You know those impossibly strong, incredibly lightweight materials that make up everything from the jet you fly in to the spacecraft heading for the stars? Well, creating them is a science of absolute microscopic perfection. One tiny mistake, and the whole thing can fail catastrophically. Today, we're going to go inside the very machine that forges that perfection. But first, I've got a question for you. What's the real hidden enemy lurking inside an airplane wing? It's not turbulence, it's not metal fatigue. Nope, it's something microscopic, totally invisible, and if you don't stop it, it's utterly destructive. We're about to find out exactly what it is and how we fight it. So here's our game plan. First up, we'll talk about the quest for these perfect composite materials, and we'll finally name that hidden enemy. Then, we'll meet our hero, the autoclave, and walk through its super delicate curing cycle. After that, we dive headfirst into the microscopic war on voids, figure out how to master the variables that decide the battle, and finally, we'll look at the hidden stresses that stick around even after the fight is won. All right, so our story really kicks off with this quest for flawless materials. The goal is simple: create one solid, perfectly unified part. The problem? Tiny bubbles, these microscopic imperfections, can get trapped inside, and each one of those bubbles is a weak point that can compromise the entire structure. And there it is. That's our hidden enemy, voids. Now, these are not just little pockets of nothing. They are pressurized traps full of gas or moisture that get stuck during manufacturing. And getting rid of them, that is the single most important goal of this whole process, period.
So, how in the world do you fight an enemy you can't even see? Well, you bring in the big guns. And that's the hero of our story, the Autoclave. This machine is basically the ultimate weapon in the war against voids, designed to forge perfect parts under some seriously extreme conditions.
The easiest way to think about it is like the world's most intense, high-tech pressure cooker. It's this massive, sealed chamber that gets filled with an inert gas like nitrogen, cranked up to over 600 degrees Fahrenheit, and squeezed with up to 150 pounds per square inch of pressure. It's that brutal combination of heat and pressure that cures the material and literally squeezes every last imperfection out.
And this thing is so much more than just a big tank. An autoclave is a super complex machine with all these systems working together. You've got the main pressure vessel, a sophisticated control system that's the brains of the operation, a gas system to move all that heat around, and a totally critical vacuum system to pull unwanted air and other nasty stuff right out of the material. They all have to be in perfect sync.
Now, you can't just throw a part in, slam the door, and push a button. The whole process is this carefully choreographed sequence called a cure cycle. It's this delicate dance between time, temperature, and pressure. And believe me, the exact steps you choose make all the difference in the world.
So let's look at the classic old-school way of doing things. You'd start heating the part with only a vacuum applied. The thinking was, let's use the vacuum to suck out any moisture or trapped air before we bring down the hammer. The full, heavy-duty autoclave pressure didn't even get applied until 2 hours into the cycle, right before the resin really starts to harden.
But that caused some problems, especially if you were trying to cure a bunch of different parts at once. So the modern approach? It completely flips the script. Now you apply significant autoclave pressure right from the get-go. This helps everything heat up more evenly and, most importantly, it suppresses those voids from the very start. It stops the tiny bubbles before they can even get a foothold. And that brings us right to the heart of it all, the actual war on voids. And this isn't just about big external pressure. No, this is about a microscopic battle of pressures happening deep, deep inside the material itself. Really, it all boils down to one simple formula. If the pressure from the trapped gases inside the resin, think moisture turning into steam, becomes greater than the pressure of the liquid resin around it, a void is born. And once it's born, it just keeps growing. This quote right here absolutely nails the key concept. It's not the 100 psi of pressure in the big autoclave chamber that matters most. It's the hydrostatic resin pressure, the actual, real pressure inside the liquid resin. That's the force that keeps gases dissolved, just like the pressure inside a can of soda keeps it from fizzing. You lose that pressure and you get bubbles. In our case, catastrophic bubbles. To really wrap your head around this, let's use this fantastic analogy. Okay. Imagine the composite material is a piston. It's filled with liquid resin, and there's a spring inside that represents the solid carbon fibers. Now, when you first apply 100 pounds of force, that's our autoclave pressure, the liquid resin is holding up that entire load. But then you open a little valve and let some resin bleed out. As it leaves, the spring, our fiber bed, starts to compress and take on some of that load itself.
So as more and more resin escapes, that fiber bed carries more and more of the weight. And this is the danger zone. If too much resin bleeds out, the fiber bed compresses completely and ends up supporting the entire load all by itself. And the result? The pressure in the liquid resin plummets to zero. With nothing holding it back, any trapped moisture flashes instantly into steam, creating massive, part-killing voids. So you see, the whole game is about preventing that pressure drop. And to do that, you have to master a whole bunch of interconnected variables where honestly, even the tiniest changes can lead to huge problems. And the difference in the final product is just stark. I mean, look at this. On the left, you have a controlled bleed. Just enough excess resin is removed, the pressure stays high, and you get a perfect, strong part. On the right, you have an overbleed, maybe from something as simple as a leaky vacuum bag. The resin pressure crashes, and you end up with a part that's just riddled with voids. It's literally night and day. You know, the thickness of the part itself plays a massive role too. This chart shows it perfectly. In a thin part, say 10 layers, the resin can escape pretty easily, and you see a big drop in pressure. But in a thick 40-layer part, it's way harder for the resin in the middle to find a way out, so that crucial hydrostatic pressure stays high, almost perfectly matching the pressure in the autoclave. And the crazy thing is, this battle starts long before that autoclave door ever closes. If the raw material is too sticky, it can trap air as you're laying it up. If it's absorbed moisture from the air in the room, well, that water is basically a ticking time bomb. Even the tool the part is built on has to be perfect, otherwise it can create little gaps for the resin to escape through. Okay, so let's say you do everything right. You've won the war on voids. You pull a beautiful, visually perfect part out of the autoclave. The fight's over, right? Not quite. There's one last, hidden challenge still waiting for you. As that part cools down from a blistering 350 degrees, a brand new conflict kicks off: residual stress. You see, the resin wants to shrink a lot as it cools, but the carbon fibers inside it, they barely shrink at all. This creates a microscopic tug-of-war throughout the entire part, locking in stress that can cause it to warp or even develop tiny microcracks down the line.
And this isn't just some theoretical problem. It has a very real, very visible effect called spring-in. If you make a part on a perfect 90-degree tool, those residual stresses will literally cause it to warp inward as it cools. You take it out and measure it, and it might be 89.1 degrees. The part has literally changed its own shape after you finished making it. Which brings us to our final, mind-bending thought. The engineering challenge here is just immense. You've just fought a microscopic war against voids, using incredible machinery and ridiculously precise timing. You won, and your prize is a brand new puzzle. How do you design a perfect tool to create a part that you know, with absolute certainty, is going to warp into a completely different shape the second it's done? That is the beautiful, frustrating, and amazing complexity at the very heart of making things today.